Okay, now that's all set up, and it's time to do the usual thing that I do. Okay, so it's possible you did this already, but I have to find my website, which I find by looking for Calvin Willamette. Is my font too small? Can you see that okay? I'll try and keep the zoom appropriate. And is it too bright in here? Probably not. It would be too bright over there, but it's not too bright over here. Okay. So we go to Calvin Willamette courses. You are all machine thinkers. And here's where we are. I think today is Thursday, 8/21. Does that sound right to everyone? 21st day of August, and we are going to learn Python. Okay. Well, that sounds fun. I think I'm going to go slides mode. These slides will necessarily start at the beginning, but you can go over here and start at Why Python. This is where to begin today. Like I said, in the college colloquium, I'm expected to teach you something as an avenue for teaching you how to learn. I've decided that thing is Python. I hope you're into that. Why Python? So there's a lot of reasons other than that it's free, but ultimately because it's free. I was started the big push, and I'm not sure when you went to school, but at some point in time, people realized textbooks cost a lot of money, and this was generally considered bad, right? You don't necessarily want to charge someone to have an education. That leads to some negative social effects, right? A lot of the early scientific computing, so if I'm trying to do any form of science, right, and any form of mathematics even, it's like, well, you have to go buy this thing called MATLAB, which I think stands for like Mathematical Laboratory, and it costs like $1,000 a year. And usually it doesn't cost people money, because usually you work for Hewlett Packard and they just buy the license for you, but while you're a student, it was a real impediment. Separately, when I was in high school, everyone had to go out and buy a TI-84 Plus Silver Edition to take calculus, and that cost some number of dollars, right? It is not true that everyone has a computer, though it does seem to be the case you all have computers, and I don't really know how that happened, but now that you have them, there's this free way to do calculations. It is very widely used. I sat in a math department faculty meeting last year for some reason. I was there probably asking them for a favor. And they took notes that were partially in English and partially in code, because sometimes there's things that are easier to express by writing an equation than there are by writing words. If you're surrounded with people that all sort of know the same way of expressing and communicating and thinking language, oftentimes you can save a lot of steps. Python, I believe, has become so ubiquitous, it's sort of becoming one of the languages that are used for communication in data-driven disciplines, right? So people often talk about something like a data frame, or there's also a computer science notion of a dictionary. These come up almost in regular conversation in things like healthcare analysis, Census Bureau, things of this nature. It's very flexible. I'm going to teach you a very specific subset of Python this term, which is the Python that's used for science. It is also used to make web servers. It is also used to make video games. It's also used to make the most recent job posting I saw for Python was someone was using it to control robots in a manufacturing setting where the robots were making computers. Do you have a question? Okay. Python is relatively easy to learn, and I need to motivate this a little bit. The languages that were popular in education before Python were designed to be easy for computers to use. There's nothing wrong with this, right? Python is designed to be easy for humans to use. That doesn't mean it is easy. That means it's easier, right? So I think the barrier to entry is a lot lower. I think you will all learn it quite well. And then Python is very powerful. It's become several times faster in the last couple years due to a lot of investment going into it. So now we can actually use it to answer some sort of numerical and mathematical questions that were difficult and expensive to answer earlier. One of those examples is the climate models that we learned about last time, right? So it is a new technology that we can do that level of scientific analysis. Why not Python? The real competing standard for Python at this university is the R Project for Statistical Computation, which is a domain-specific language used for statistics. You will meet many people that know R. Are any of you going to study data science? R is used at least in the National Institute of Health and I believe it is used in the UK in the health sector. I don't know how common it is. That is sort of one of the scientific computing competitors. There's also this language called Julia, I don't know anything about, which is faster and harder to write. And then on the flip side, if you're building software, it's mostly competing with JavaScript, which runs in the browser, so there's these other languages. Those are programming languages, and I'm a computer science, so I like to talk about this. There's also this thing called Excel. You all heard of Excel, Google Sheets, right? A lot of people like that. I don't like that because I perceive it as difficult to use automatically. I learned to use Excel for the first time in like 2003, and every time a new version of Excel came out, I had to learn where to click the different buttons on the screen. Separately, I also learned to program with if statements and for statements in 2003, and I haven't relearned any of that stuff. That's the exact same as it used to be. I'm going to introduce, sort of over the course of this term, a series of Python libraries. You don't need to know any of these. I have to teach you something, so I picked out what I hope are the most potentially interesting things to use. But I'm going to teach you numerical, scientific, and symbolic ways of doing calculation. We're also going to do some plotting tools. As a rule, our impression in sort of the education space is that students like writing code that creates images, and so oftentimes we use graphs for that and data visualization. So we will do some of that. And I think I have some cool data visualizations for you, and you can tell me if you think they're cool when we get there. To begin with, we're not going to necessarily start with a data visualization. We're going to begin with a running example. This running example is motivated from a very specific case, which is that around this time last year, I was on the STEM Fellows Discord, which you have all joined, right? Okay. Have you joined it? You will join it? You haven't joined it yet?
No. Where would I find that?
It was in the summer homework email. Maybe I'll send one out again, like this evening or something. Do you have the link? Can you send out a link to them now? We'll make sure you're all in there. So there's two sections of the STEM, whatever we are. Do you know what we are? What it's called? STEM, right? And the other one is taught by Allison Fisher, who is better than me, and that burdens my soul, right? So if I have higher participation in my section in the Discord, that will be like, so it would be a personal favor to me if you log in there and like post emojis every day, right? Like, I don't care what you say. That's not true. For the most part, I don't care what you say. Just like get in there and like do damage, right? Okay, so I think that should be a good goal for us this semester, and I'll try to occasionally remind us to do that. Okay, so anyways, one of the students that was in this Discord, it's a very interesting Discord because it's myself, two chemists, and a physicist. But you're all like huge nerds, so you take calculus at some point. Who loves calculus? Can I get a whoop whoop for calculus? Wow, not a single, that was like a very half-hearted whoop whoop. Anyways, you will learn to love calculus. Trust me, everyone loves calculus. Right?
Oh, yeah.
But yeah, okay, all right. Okay. Am I the only person in here that likes calculus?
No.
Here, we'll do some calculus real quick. This is not part of the lecture. Okay, so this is a curve, right? Yeah, let me take a tangent line with the curve. It's calculus, right? Like, that was fun. I had fun doing that, right? Yeah, see? Okay, all right. It's not that bad. It can't hurt you that okay. It can be involved in hurting you, but it can't hurt you itself. It's an abstract concept, right? So, some student was taking Math 150, differential calculus with pre-calculus, which is sort of the first math class you take here. And I think had a math homework problem. I think in these slides I say I thought it was in a physics class. I found out that's not true. But it's the only example I know of where someone went into the STEM Fellows Discord and asked for help on a homework problem that I could solve the answer with Python. So I'm going to use that to teach you this. And the thinking is, I've taught many classes many times, and students often ask, how am I going to use this? And so now the answer for what I teach today is this will help you in one of your other classes. Probably, at high probability, right? And so we're going to do that. I'm going to take this example. I'm going to use a step-by-step solution where I'm going to solve the problem, and I'm also going to teach you Python while doing it. And then I'm going to give you a dramatically harder version of the problem and make you work on it together tomorrow, okay? This dramatically harder version of the problem I actually didn't know was harder because once you know the answer, it seems easy, but I gave it to my partner who has a doctorate in chemistry, and she couldn't solve it. And she was mad at me for making slides that she thought didn't teach her enough. So I thought it was a perfect brain teaser for you on your first day of class. Okay, here is the problem. So this is what I call a piecewise function. The first time I saw a piecewise function, I believe I was taking a class called AP Calculus AB in 2009. I don't know what things have changed since then. The way to interpret this following equation on the board, and this equation is useless, but I'm going to apply it to something in just a minute, is this is a function expressed over x values. The x values are numbers. We don't say that. You just have to know that. And one of the ways to tell that is they're multiplied by numbers, right? So I take an x value, which is just some abstract notion of things. In a minute, it's going to be dollars. Right now, it's not anything, right? And I check my x value to see if it is less than 4, greater than or equal to 4, and less than or equal to 8. So, for example, 6, and also greater than 8. And I don't know why big mathematics did this, where you have to check over here before you decide which side you use here, because I read right to left. But it's possible this was developed initially in a language where you read left to right or something. I don't know. Wait, I read left to right. Which one's right?
We read left to right.
You read left to right?
Yeah.
But you're facing a different direction than me, so your left to right would be my right to left. Right?
Yeah.
So I start reading on the right side of these slides, and then I read to the left of them until I turn around, then it's the other direction, right?
Yeah.
Someone was talking about perspectives yesterday. Who was that? Yeah, you got me. Okay. Okay. So anyways, that's how this works. So for a fun experiment, what is f of 2?
41.
I think I believe you. That sounds right, doesn't it?
Close enough.
Can you tell me why it? Do you say
never
okay?
mind. He said close enough, so I feel 2 to the power of 2 is 4 times 9 is 36 plus 5 is 4.
That sounds pretty good to me. Yeah, I like that. Okay, we're gonna say good job, and we'll verify it later. Okay. Thank you. Okay, so anyways, you didn't have to find 2 at all. You had to find -1, 4, 5, 8, and 11. One of the benefits of that is I think all of those have a solution that is smaller than 20, which is usually easier for humans to think about. The quick, I think it was 41. That was very impressive. Good job. I think it is very interesting that someone's multiplying 9 times x squared. That number gets very big very quickly. So there's a local maximum, or I think it's the global maximum of this thing on the positive numbers is at x equals 3.99 repeating. And it's like some enormous number, right? It's 4 squared, which is 16 times 9 plus 5, which is a large value. In the interest of this not being fake, right, I tried to figure out what the most important thing in the universe was, and I think it's the economy. Does that sound right? Yeah. Hopefully not, but I think that's what it seems like, right? And so then I tried to figure out the most important thing in the economy, and it seems to be taxes. Does this sound right to anyone? Okay, so it turns out taxes are a piecewise function. And this was not at all a contrived example. I didn't make this up. So this is some version of the United States tax code. There's really extreme aliasing on that because there's something wrong with that projector. But if you're following along with the slides, you can see it. And also these numbers don't exactly matter. But one of the things that's interesting here is you can say if you're single and are any of you currently married? Okay. Yes, congratulations. Okay, so you might be either married filing jointly or married filing separately, right? So you would have to decide that. If you're single, and so this is a great reason to not date in 2025, your taxes are easier, right? Okay, so if you're single, you can just look up how much money you're making in a year, and then you can compute the marginal tax rate, and that will tell you how much money you have to spend, right? And if you don't know, that's not the button I meant to press. If you don't know, I think a fun thing we can do, and I should show you some information. What buttons am I pressing? Oh, I changed my operating system over the summer. There we go. Okay. Some of you are probably thinking about what major you want to do, and I found an interesting graph the other day that was also shared on the STEM Fellows Discord, and I'm going to attempt to type into the search bar the search terms that are going to find that graph. I think it was labor market outcomes, new graduates. Oh, there it is. I was looking for it. New graduates by major, Federal Reserve. Okay. So this is one way to estimate how much specifically people that are about to finish college are going to make. So this is you in 4 years, I think, unless you graduate early, which talk to me. We should get on that. As you know, at various points in time, the economy has been good or bad, even though it's the most important thing. So here in 2019, probably something happened. I have no memory of that, so that could have been anything. In 2008, something also happened. And then way back here in 99, that was the dot-com boom. That was my people. That was the computer scientists screwed everything up. So I'm personally responsible for this one. I like looking at labor outcomes by major because that's fun. And then I just always sort the early career by low to high. And the reason I do that is because then computer science is tied for first. But we have really bad unemployment right now. If you search by unemployment, you get nutrition sciences, of course. Salaries are a bit lower in that field, but civil engineering is way up here at like very low unemployment and very high salaries. So you can look into any of this. And this is a fun thing to do. So data science, for example, is not on here. I don't know, we need another major. Let's look at physics. Everyone loves physics, right? Any physicists? Not a single physicist? Okay, well, then we can pick on them. Okay, so here's the physicists. They are expected to make $70,000 a year, and they have a 7.8 unemployment rate. Oh my gosh, that's terrible. Oh no, anthropology's down here at the bottom. I'm sorry. I didn't know that was going to happen. I would have done something else. Okay. Oh no, chemistry.
I already lived it.
Oh, computer science is also on the bottom. Okay, so don't major in STEM. Become a special education teacher or an animal and plant. Oh no, a bunch of you are biologists, right? Animal and plant sciences. That could be you. That could be you. Okay, so we're all safe. Okay, so, but there could be, this could look like a bigger wage spread than you think, because actually this $80,000 goes into this thing and gets reduced by different percentages, right? So there's sort of an inflection point in here at $37,000, right? And so it's good to keep all of these things in mind. Okay, now I'm going to attempt to make this full screen again because I think it looks weird when you have this thing at the top. And I think I do that by hitting function F11. Okay. So it is worthwhile to think about, given either the easy piecewise function or the more challenging tax bracket function, how we would solve the problem of, given some income level or given some numerical value, what is the output of this function, right? You can think about what steps you would solve, and you think about what would make solving it hard. The earliest computer programmers were actually thinking of this in a very specific way as telling a human instructions, because computer referred to a profession and not a piece of technology for many years. So you would actually dictate to someone the steps they should take to solve a problem, right? And so if I were to describe to you how to solve a piecewise function, well, you actually saw me do that already. I described it to you. I attempted to program you as humans how to do that. Now we're going to attempt to program computers. My personal bias is that it is easier to program computers than humans. And so that's why I started liking computers a lot. So let's step through an example, and let's see how I can get this to work. I'm going to zoom out. Am I going to zoom out? There we go. Okay, so I want to do this using Python, and I'm going to demonstrate how to do this with Python. So one of the first things we can do here is that we have 9x squared plus 5 for x less than 4. And our first value for which we were supposed to solve this function was x equals negative 1. So I perform a substitution. I substitute in x for negative 1, and I multiply 9 times negative 1 times negative 1 plus 5. I want to point out that we have some sort of lingering complexities coming in from computing already, which is that I do want to write x times x instead of x squared, because I don't want to talk about how to square numbers yet. But I hope we can all agree 9 times negative 1 times negative 1 plus 5 is the value of this function if the input is x equals negative 1. Do we all believe that? Can I hear like some heads rattling? Any of you skeptical? That's a thumbs up. That's going, yeah, that's probably a yes, right? Okay, very good. So anyways, that evaluates to 14, which you can see right here. A lot of things are going on this slide, but one of the things I want to introduce for the first time is this is the first time I'm showing you Python on these slides. I have a line number here. I have a bit of Python. I have a way you can copy paste this value. So you can put this somewhere else. I suspect Google can actually figure that out as well. And then the Python evaluation of this expression pops up under the box. So these slides are actually executable Python code, and they're executable code in the sense that I'm going to ask your final project to be of this format. I will teach you how to do that. Just be aware of what you're looking at. Okay, next. So in Python, that's not what I meant to do. We can do a lot of the things we can do on the TI-84 Plus Silver Edition calculator, the graphing calculator I had to purchase to take my AP classes. We can do many of the same operations we can do in MATLAB, the $1,000 piece of software I had to purchase during my undergraduate. And we can do a lot of the same things that I did in this little magical place called elementary school. I remember learning multiplication for the first time in 3rd grade, and it seemed really hard at the time, but I do in fact know what 6 times 7 is now. I'm like almost 100% sure it's 56. And one of the other things I learned is at some point in my life I started teaching and never attempt to do multiplication from students. It's dramatically harder to do it up here. So here are some examples of just some things I can type into Python. I can say 6 plus 3, 6 minus 3, 6 times 3, and 6 divided by 3. And these are all expected, but we are also once again teasing a little bit of lingering complexity, which is that these numbers don't have decimal points on them, and this one does. That should make you nervous, and you should be suspicious about that, and you should have questions about it. And we should come back to it later. So we're going to begin by doing this thing called evaluating expressions. Expression can mean many things. How many of you have a facial expression at this time? Yeah, there. Very good. My favorite facial expression is like quixotic or something, or where you look, perhaps like vexed, maybe something like that. And there's many forms of them, but we can put many expressions into Python. And at this point in time, I'm going to open the Python window and start typing these things into them, because this is what a Python window is supposed to look like, and I want to show you an example. So in order to do that, I'm going to exit full screen. I'm going to hold down, on my device I have this Windows key here. I don't know exactly how this will work on Mac or Chrome, but I hold down that key and press the left arrow, which cuts my screen in half. I'm going to open the search bar, or the, I don't know, it's called like Spotlight bar on Mac, and I think it's called the Start menu on Windows. I'm going to get this little type to search thing. I have neither Mac nor Windows because I'm a huge nerd. I have something called Linux. Have any of you heard of Linux before? I'm sorry. Yeah, I know.
What OS are you on?
This is just Ubuntu. Yeah. Anyways, in the search bar, I'm going to type terminal, and I'm going to open terminal. And this is my command line. Did they use the command line earlier with Python?
No.
Is command line new to them?
Use what?
Did you use the command line in the earlier session?
Yeah.
Okay.
Terminal, we'll just type in terminal, yeah.
Perfect. Thank you. So I'm doing that same thing. Good job. Good job.
Everyone's got it.
Well done. I'm also going to make the terminal larger, am I? Maybe I don't know how to change the view size of this. Preferences? It looks small to me, right?
Mm-hmm.
What if I'm clever enough to change that? I might not be.
So is expression just basically what the code looks like before it's executed, or?
Depends on what you mean by look, I would say. It is the symbols that represent the idea of the code, which we can think of as visually, but it doesn't have to be visual, right? So if I had a screen reader or something, I'm just going to change my scale. Is that going to work? Everything could break here. Okay. All right. So I am going to demonstrate a way I would use Python to solve this problem. The first thing I do is blah, blah, blah. I set up my screen with my web browser and my terminal. I would encourage you to follow along if you're doing this. I'm going to type either Python or Python 3, depending on my operating system. I'm typing Python 3. On Windows, I expect you to type Python. On Mac, I expect you to type Python 3. On Linux, I expect you to type Python 3. I don't know. But within Python, I can type these same expressions. And an expression is a bit of text or a symbolic representation of an idea that I can submit to Python. and it will be evaluated. So an expression is something that can be evaluated. 2 plus 2 is an expression. And I can submit 2 plus 2 to all of you, and in fact I submitted the 9 times 2 squared plus 5 to you. But I can also submit those same expressions to the terminal. Historically, the reason this is called a terminal is in the olden days there used to be one computer on campus, and you would not actually have access to or control of the computer itself, but you would have something that was called a terminal, which was access to that computer, and you would get to use fractional parts of the computer at a time. So in the olden days, in the ancient days of yore, in like, I don't know, the 60s or something, like when the Beatles were touring, this terminal would be running on a different remote computer. In modern times, it is running on our current local computer, but it doesn't have to be, right? So this is an example of an expression that I can type in, and I can type 9. So an expression doesn't have to be changed when it's evaluated. The value of 9 is 9, but the value of 9 times 9 is 81. And then I can also do subtractions. And I can do sort of all of the expected arithmetic operations. This oftentimes seems like a little bit useless to people, but I actually am not super good at computing 12 times 34 mentally. That takes me a long time, and it does not take the computer a long time, right? And in fact, you can put quite large numbers in here, and it can solve them very quickly. And so this became really useful if you were trying to do anything that wasn't easy. And originally had applications in things like space science and so on, and is now just used for everything. So that's what I'm doing. I'm going to introduce another wrinkle, which is that I think it is not that complicated to necessarily type in the things that you typed into a Casio or TI calculator at various points in your life. But that's not quite programming yet. That's not quite scientific computing, so we're going to go one step further, and we're going to use conditional execution. We're going to take different actions based on different conditions. And the first case of conditions we're going to look at are the same conditions we saw in the piecewise function. When you as a human looked at the piecewise function and I gave you the number 2, you had to decide if it was less than 4, between 4 and 8, or greater than 8, right? And we can actually ask our computer to do the same thing. So I can say is 1, negative 1, less than 4. And I will get back a true or a false. What this means to us is a few things. It means we can determine if statements are true or false. We can, for example, see if 9 times 9 is equal to 81. And we can also see if it's equal to 80. And it also means that not every expression turns into a number. I believe on my graphing calculator everything turned into a number or perhaps an error. I think you got an error if you divided by 0 or something like that. We have a little bit more sophistication here. We have things other than numbers we can work with. There is also this kind of annoying thing I see, which is the idea of accommodating keyboards. There are expressions that I can write by hand. You all loved calculus, right? I seem to remember that. So I can take the interval from 0 to x of x cubed dx. I don't have any of these keys on my keyboard, right? So I have to make some accommodations. And the first accommodation we've seen that we need an example of is this less than or equal to sign. Would we call this less than or equal to? I never know. People say greater than or equal.
Less than.
That's the greater than sign, and this is the less than sign? No, that's an X. Never mind. Don't look at that. Okay, so I don't have that key on my keyboard, but I have the ability to type it in. Because 4 is not less than 4, but 4 is less than or equal to 4. Wow, that is so small. Has that looked that bad the whole time?
Yeah.
And none of you said anything?
I got used to it.
I feel like I should accuse you all of being cowards. I'm not going to do that, obviously, but I feel like I should. I'm going to increase my size again and see if that helps. Do I remember how to do that? Display. No. We'll see if this looks better. Ooh, it's thinking. Always dangerous. When the machines think, right? Right? Hey, come on. I'm doing my best here, right? Okay. Live streaming. OBS. Ooh, can I not? That's frustrating. Okay, can I? It's still clipping. How annoying is that? Let's see. If I change that. Okay, I might just have to clip the side there. And let's see, how visible is that? I think that's basically visible. Wait, it looks better over here, right? 0 looks better than... Let's change sides.
It looks better in like the center than the outskirts.
Or both of the sides are bad? Oh yes, because Anne looks bad. That's so odd.
But if you put the black thing down in the back.
Oh, okay, that's a good idea. I took the Amtrak bus down here and it had these really nice blackout shades and like the sun wasn't bothering me. Wait, do I know how this works?
Yeah.
Why is it making that sound?
Also, it's down like hell.
I think it's just a problem with the projector lens, probably. Some sort of distortion.
But this works better. I can see it clearly.
Yeah.
I would like this to work better.
I think you broke those.
I break lots of things. Okay, so we can do equality and inequality testing. This oftentimes also seems like a little bit too easy. Oh, I'll do bigger things. What is 45 times 67? Is that greater than 10,000? Just like the fact that we can't do it instantaneously is so interesting, right? Like, it's so easy to do. I could approximate them, right? Like, I know both of those things are between 0 and 100, and I also know that 10,000 is 100 squared. So I knew that that number was smaller. But still, just looking at it, it took me a minute to realize, right? We should never have to think about tedious arithmetic again unless we want to for fun, right? That's why computers exist, right? And once we don't have to think about arithmetic, we can do calculations very quickly about very interesting things. Like, you know, I think a lot about, for example, calories, right? So I try and eat a specific amount of food. I like weighed myself today, and I was like losing weight, so I had to like go drink water or something, right? It's so much easier when I don't have to do any calculations myself, because for some reason there's like 7 days in a week. There's like a very odd number of days to be in a week, right? And so if you're like at the grocery store figuring out how many calories you need per week, you're like multiplying things by 7 or 21 if you're doing it per meal. It's like your computers can do that so quickly. And you can do them in Python instead of using the calculator on your phone. Okay, so we can do less than or equal. We can also do 2 of these at a time. This is what I'm pretty sure is true. I was pretty sure 56 times 67 is between those 2 values. I didn't know for sure, but I can check. It's this much, which I wouldn't have guessed, right? I do want to point out it is important to what I've learned from writing code in front of people, that's you, is that because I've been writing code for fun for 10 years, which is how many years ago I was in the position you're in. Is that true now? No, because I've been a professor for like a million years. 14 years. Pretty soon my code will legally be able to drive. That's fun. Okay, and so it is important to show that not everything you type into Python instantly evaluates to something useful. And something I did a lot when I started coding is I didn't remember which side the equal sign was supposed to be on. And I also oftentimes leave out that I do not type those 3 little, I think those are greater thans, right? That just represents Python is asking me a question. So it's important to show what this looks like. So I can say that 4 is less than or equal to 5. Ooh, I bet I can't do it with the space, right? That's not allowed. I can do it without a space, but I also can't put the equals before. The reason this was significant to me is when I was taught this, I did learn 4 less than or equal 5. I learned this less than or equal first, and I assumed it was actually supposed to look like an arrow. So the next thing I did was I assumed that 5 greater than or equal to 4 would be expressed this way, which is not the case, and that's what's represented over here. For whatever reason, we always put the equal sign second. This is just a social convention. This is the same social convention as people computing multiplications before additions, right? So look out for that. If you type things that are odd, try and find an example, try and find a solution. Some people are asking generative AI for this. That is correct at the easy things and not at the hard ones, basically. Okay. One other thing I want to introduce before we can actually solve the piecewise function example is one of the first things I said in the piecewise function is we set x equal to some value. The way we do that in Python is we use the single equals sign. And then separately I said we can ask the computer questions which it can answer. And I did that using the double equals sign. This is weird and strange. But if I say x equals 1, I do not get true or false or anything. What I've actually done is I've told the computer to hold the value of 1 in x. And I can set x equal to anything I want. And then I can use that value later. This is distinct from checking to see if some value is equal to something else. So if I say 1 plus 2 equals 3, that's against the law because I cannot change the value of 1 plus 2. But I can check to see if the value of 1 plus 2 is equal to 3. So this is single and double equals, and this will be useful for us when writing a piecewise function. I'm just not happy with how these slides look right now. Okay. So we're going to touch on expressions that don't evaluate to a number and also on assignment. And we're just going to do this briefly, and then you're going to get used to them over the course of the term just as a useful technology, not as an independently interesting idea. So sometimes a Python expression becomes a numerical value. 7 plus 7 is a numerical value, is a numerical value 14. Sometimes a Python expression is a Boolean value. I think this is named after someone whose name was Boole. I don't know why they're called Booleans. I think it's actually the philosophers started calling them Booleans, and then the mathematicians did it, and now we're stuck with it. So for whatever reason, true or false are referred to as Booleans or bools, B-O-O-L. And that's just true or false. So you can write different questions and you can get different kinds of answers. This should be familiar to all of us because you're accustomed to probably things like multiple choice and free response answers, right? So this is not that strange. There is a strong usefulness of Boolean expressions in particular because sometimes we want to figure out something and then take a different action based on the result. A good example of this is we were discussing the opening days schedule recently, and I had to buy an Amtrak ticket based on when the opening days schedule had me here teaching, which is so much harder than I thought it would be, and I could not ask a computer for the answer. So we're going to perform some calculation and then take some action based on the result. So let's take a look at an if statement, and this is our first multiple line statement. So I'm going to write if. I'm going to write some expression that evaluates to either true or false. I'm going to place that expression inside of parentheses, and I'm going to punctuate that line with a semicolon. And then underneath that, I'm going to write a print statement. So we can print values the same way we can just look at the value directly. And this usefulness of this is in olden days before monitors existed. Sometimes you would put in a lengthy sequence of code and then only print out the last result. And that's what the abstract idea that is at play here is corresponding to. So let's check to see if 1 is less than or equal to 1. We will punctuate that line with a colon. I think I said semicolon before, I didn't mean that. When I press enter, I automatically get those 3 dots. I did not type these 3 dots. There's also a space there, it's not visible. And then my cursor is 4 characters over. I have to indent my next line. It is the opposite of paragraphs, where we indent successive lines rather than the first line. And then I'm going to print something. In this case, just 2 plus 2. I had to print and enter twice, and then I see the 4. We can also change this around. I'm going to press the up arrow on my keyboard to get some previous code. I'm going to change this to less than, so this statement will now be false. and I'm going to print 3 plus 3. And this time I will not see an answer because I am not going to print out what 3 plus 3 is because this is false. Good example of this programming in real life is last time I went to the grocery store, my partner was out of vegan Greek yogurt from Kite Hill. I remember, right? So it was Kite Hill vegan Greek yogurt. I don't know why I remember that. And I got very specific instructions because I guess prices fluctuate. This is one of those things like, so we were looking at labor market for graduates. Also, there's like inflation, right? I was instructed to purchase Kite Hill yogurt if the price was less than $7 per some unit. I think it was like 4 servings for less than $7 or something. So anyways, a human dictated to me an if statement. It was like, while you are at the grocery store, if this value is less than that value, perform this action. And unfortunately, I misremembered that the price was between $7 and $8, and I purchased yogurt for more than I was supposed to, but it was only by 12.5%, so I think that's okay. But this is like a naturally occurring thing that occurs in real life. I don't know that I ever learned how to do this on a graphing calculator. I believe it was probably possible, but I never looked into this much. So this is sort of the beginning of computers making decisions for us. You could argue at this point in time, and I don't know you'd want to, that this is the first case of a machine thinking, right? Given some conditions, it takes some specific action. We're going to use this to construct our piecewise function, and we're going to do this in not particularly the most complicated way. These are, to me, if statements, and I can simply write out those if statements, and I'm going to do so. I'm going to do this again. And so I can say if -1 is less than 4, I'm going to print 9 times -1 times -1 plus 5. And that will work splendidly. I can also put in a value other than -1 there, so I can put in 4. I pressed the up arrow. I'm going to press the up arrow again. I think these -1s are supposed to be 4. That doesn't give me anything, because 4 is not less than 4. But we can also check other things. We can also say if 4 is less than or equal to 4, substituting 4 here, less than or equal to 8, then I'm going to print 9. And so this isn't quite a solution to the piecewise problem yet, but this is a solution to each individual sort of slender piece of the piecewise function. It's a solution to each row. And I just need a way to compose these together. It is somewhat obnoxious that sometimes I get a solution back and sometimes I do not, so we're going to solve that problem here together. We're going to do that using else. When I was at the grocery store, I did get an else clause. Instead of, the reason I mentioned Kite Hill, I think there's another brand, Siggy's. Siggy's makes like Icelandic yogurt, which I don't know what that is. Does anyone in here like super into yogurt? Okay, that was good. It seems like a very complicated world out there. There's people that make their own yogurt. We actually have like a yogurt culture starter in our freezer that we're scared to open. But you're all biologists, so you should all culture your own yogurt, right? Okay, so we get to use the else clause. And the else clause was if Kite Hill greater than 7, then Siggy's, right? So we can write that expression out here. Let's look at an example. I don't know what I'm typing. Okay, so we're going to say if 1 is less than 1, I put in too many spaces, I'll fix that. Print 1 is less than 1. If I want to print out words, I have to put them in quotes. That doesn't matter, we'll get to that someday. 1 is not less than 1. And we can see that 1 is not less than 1. That seems true. I think that's true. Does that seem true to everyone? Can press some up arrows, can change this to less than or equal. I don't know. I don't think that's true. But whatever, I did. So we can use these else statements to construct more sophisticated operations. Usually, I think people use this to check to see if numbers are odd or even before cutting them in half. Sometimes you might have to do rounding, things like that. And then we also have elif, which is that the computer scientists were tired of writing out else if, and so they combined it into one expression. And elif allows you to have more than one condition. So for example, I've never gotten one of these delivered to me orally in my experience. But I think I do this sometimes in academic advising. So I was just emailing one of my students from this class last year, and I said, if you are willing to take IDS 240, Scientific Communication and Outreach, which meets 6 hours of class time, which is a large number of hours beginning at 8 a.m. on Tuesdays, which many students do not want to wake up at 8 a.m., enroll in that class. Otherwise, enroll in GCS 101, Global Cultural Studies 101, which fulfills a variety of your graduation requirements, if there are seats in that section. Otherwise, enroll in most likely a music class, Music 299, topics, listening, where you learn how to listen to music through critical lenses, right? So that was a case where I wrote an email to a student that had taken this class that used an else if, right? We can also do this mathematically, and we can also do this in Python. And here's a way to write it. I'm going to cheat now. I'm going to copy paste. I'm going to click this little button here. It's going to copy to clipboard. Then I'm going to right click over here, paste this in, and I can evaluate the expression. And I think I can do the same thing over here, but I can't because I'm using too much of my screen. Can I zoom out? No, I can't. This is an example of an elif. I'm going to type one for you as well. If 1 equals 1. Oh, that's cheating. We'll say 1 is less than 1. Oh, we'll print A. Elif 1 is greater than 1. Print B. Else print C. What will I see when I press enter?
C.
That is what I will see. Yeah. No? Okay, all right. I thought that was funny. What's a pirate's favorite letter?
R.
You think it's the R, but it's really the C.
Oh my.
Right? Yeah? Okay,
Yeah.
all right.
That's a good one.
See, it's really the C. Okay. Do people still do Talk Like a Pirate Day, or do we outgrow that? It's like it just feels like it's problematic for some reason, but I'm not sure what the reason would be. So I'm scared to do it. Right? I don't have a critical analysis of whether I should be doing Talk Like a Pirate Day or not. Right? Okay. Now we're going to do one other thing, which is we're going to make our lives easier using single equals, which is we're going to use it for variable assignment. And I'm going to use that here. I'm going to write an expression once, and then I'm going to get to just change the x value and do it again. So I'm going to copy paste this code. I'm going to use, I think, Control C to do that. Can I do? Do I have to do that? Oh, I think it's Control Shift V. Yeah, there we go. And I can change the value of x. So I can say x is equal to -1. And -1 is less than 1. I can set x equal to 2. And I can see that x is greater than 1. This, to you, I hope, is going to start to feel an awfully lot like the solution to a piecewise function. Does it feel like that? How's it going? Can I get a thumbs check in? Can I get like some of these ones? Sideways, that's pretty good. Some of you are up, some of you are sideways. No one's willing to give me the thumbs down, but we've already established you're cowards. Okay, or no, we've established that I could call you cowards, but I didn't actually say it, remember? Okay, so I think this is cool. Those of you that are following along, has anyone typed something into their computer and not been able to get it to do what they wanted? Should I walk around and look at your screens? Okay, I'm not going to do that. Okay. Lastly, we're going to introduce, I shouldn't say lastly. At this point in time, we're going to introduce the other way of using equal, which is double equals, I call it equality. It's quality testing, checking to see if two things are equal to each other. The reason I just have to point this out is a common error for people working with computers is you write single or double equals and you mean the other one. So I have a slide on it. That's all. These slides do almost exactly what you think they're going to do. We can check this. I'm going to copy paste that. That's not what I meant to do. Do you ever think someone else is the person using your fingers? That happens to me a lot. Okay. X is not equal to 1. Really? What is x? Oh, it's 2. Okay, let's set x equal to 1. Then I'm going to use double equals to check. And x is equal to 1. Are for the most part you able to put code into the terminal from wherever you have it on your screen? I'm doing that with two operations. I have Control-Shift-V, because I can't use Control-V directly. You might be able to use it on Mac or Windows, I'm not sure. And then I also have right-click, which is probably Command-click on Mac, and then I do paste. And those are the ways I perform that operation. Last thing to tease in sort of this doubling sense is that previously I solved -1 squared by typing the -1 twice and multiplying it by itself. That's tedious and annoying. The way to square values is with double asterisk. The reason for this is historically complicated, and it's basically that the caret key, I call this caret, that is on my keyboard at Shift 6. I always expect that to be used for exponentiation, and it's not. It means something else in most computing languages. So we use double asterisk instead. Double asterisk is a great time to see that computers can handle pretty large numbers. It is possible to stump them with big enough numbers, though. And this is where we're going to have to actually start using scientific computing at some point. An interesting question to think about this is, how many digits do you think that number has?
We know how.
We know how much it doesn't.
We know it has more than 43,000, right? Or 4,300, right? A fun thing you can do is try and figure out how many digits your computer can handle. That's not too hard to do. So for example, we knew that 100 squared is a 10,000, because we mentioned that previously. You probably know that 10 to the 10th, I think this is 10 billion or something like that. 1,000, million, billion, 10 billion. So you can sort of just count how many digits you get, and so I think we can do 1,000 digits no problem. I think this was our cutoff, right? But we can probably do a little bit less than that. And so that's allowed. But I think separately, if you store these values, you're allowed to calculate them. You just can't show them. And I don't know how big the number you can put here is, but I'm guessing it's quite a bit larger. Oh, it started slowing down there. Did you see that? I'm going to press Enter and then think about how long it's waiting. So it is slowing down, but it's still able to handle calculations of this scale. But this is still many times smaller than taking two 7-digit numbers and raising them to each other's power. Ah, it got it. And we're not allowed to look at it. But maybe, oh, can I print it? No. Okay, well, we tried it. Anyways, the caret key is used for something else. Don't worry about it. It's not a scientific computing topic. My impression is at this point in time, we can actually finally write the piecewise expression. And I have it written here. So I'm going to go ahead and copy that in, paste it, and it is going to correctly compute that the piecewise expression, when evaluated over 11, is -9. Let's see if we agree with that. I'm going to think, what is 11? 11 is not less than 4. It is not between 4 and 8. It is greater than 8. So I'm going to take 2. I'm going to subtract 11 from 2. That is going to give me -9, and that is the same value I get over here. We can take just the piecewise expression itself, and we can apply it to different values. So I can say x equals -1, and I get 14, and say x equal, what was the next thing we were going to check? 4, and I get 9 for that. So this is a way to solve a piecewise function without doing everything manually by yourself. It is up to you whether you think this is easier at this time. I would assume this seems much harder than just solving the equation manually to you, though it could be already at this point that this seems like an easier way to solve the income tax problem, which was already quite sophisticated, right? It had many different brackets. Let's make things a little bit easier with the principle of code reuse. Quite a few times today, you've seen me copy-paste things more than once, and sometimes it breaks. I think, I have to copy-paste this, then press enter. If I copy-paste twice, it breaks, and I get a variety of errors. We don't really want to do that. As a rule, I don't love copy-pasting code back and forth. It's a little bit too easy to introduce errors. It's too hard to maintain what you're doing. It's too hard to make sure you're consistent, right? It's not the worst thing in the world by any means. You shouldn't feel bad if you're doing it right, but I do want to teach you a better way, and that better way is using the def keyword, DEF, for define. I don't think there is necessarily a close parallel to this outside of the computing space, in the sense that you have probably at various points in your life learned addition, subtraction, multiplication, and so on. These are functions. We can also think of having custom functions, and perhaps I can build square root out of things. I built a custom piecewise function. It doesn't necessarily have any meaning to it. Maybe we think of this as the functions that we graph, right? So we're going to use def to create saved expressions, so something that is going to return a value of some kind, of arbitrarily high complexity, and then we can use them more than once. So how am I going to do that? Def isn't too bad. It is similar to if, in the sense that you write the keyword, then you write a space, then you write something else. In the case of a function definition, we write the name of the function. So I can create a doubling function. Def, someone hit caps lock on my computer. And then I can double 7. This is a simple enough example, right? But they can become more sophisticated. I am going to basically, out of necessity, have to introduce a little bit of vocabulary around this. The way it is often described to do this thing, to use a function or to apply a function, is almost always referred to as calling in computer science. I think of this as sort of the same way you maybe call someone when you have a question. So my car is in the shop right now, which is why I was taking Amtrak here. Though I would highly recommend Amtrak. Train's good. I actually took the bus. The bus was pretty nice as well. I had an action that needed to be performed on my vehicle, and so I called a mechanic who actually had the requisite skills to do that, and then the action began being performed. Right? I didn't have to know how the mechanic would solve the problem. I just had to know what the name of the operation was. Then I could ask the mechanic for it, and the operation could take place. So I don't have to know how doubling works, and in fact, I can change how doubling works, and it doesn't affect anyone else, right? So my mechanic can solve problems in the manner of their choosing. And the way we call these functions is we give the name of the function, the same name we wrote after define, and then instead of putting the name of a variable inside the parens, we put the value of a variable, and this performs a substitution wherever the variable occurs in this expression, we replace it with 9. And so you know this already, but if I print 9 plus 9, typing is hard. Goodness sakes. Okay. My brain stopped working. What time is it? It's 5 o'clock, isn't it? My brain stopped working at 5 o'clock. Okay. Wow, I really ran out of brain there all at once. Okay. We also get the same 18. Okay. I think this topic is hard, so I'm going to ask for another thumbs check-in. If I ask you all to write triple, can you do it? If you had to do it, what would you do?
Normally just do def double 3 times.
Tell me what to type.
Oh. Triple. X.
I think you're correct. Continue.
Oh. Times X times X.
Like this?
Yes.
Okay. Tell me when to press enter, or should I keep typing?
Do you know shoot, what's it called? A close.
Oh, a paren?
Close
Probably?
bracket?
Yeah.
And then enter? Oh god.
Okay, so I can do this. That's cubing. That's x times x times x, right? Does that make sense? That would be cubing? I would think of this as tripling. Is that what you're going for?
Mm-hmm.
Okay. Oh, I didn't do your name today. What's the third letter of your name? Angela? Okay,
Yeah.
cool. Right, 6-letter name. Okay, yeah, no, okay, thank you. Yes, do you want to suggest?
Like define, like how we would do triple.
Yeah, sure.
So EF and then triple, and parentheses, X, parentheses, colon, and then enter, and then you would be print, parentheses, X plus X plus X, parentheses, and then enter.
We have to indent. This was quite close.
Oh, yeah.
Can you tell me about your thought process on how you arrived at that solution?
Oh, I mean, BF is defined, so basically you're asking us, like, how do you define triple X, right? So you have to first name the function, which is triple X.
Mm-hmm.
And then on the bottom, you're basically explaining what triple X means. So
Okay.
X plus X plus X is how I got to the answer.
How did you decide to use x?
It could be any variable. No?
Let's try it.
It could be any variable. It could be any letter, I think.
Do you have would you like to choose another letter? We can try.
A.
Let's try A. I think 8 tripled is 24, so that makes sense to me. So the important thing to think about in this analysis, and we had many portions of correct solutions here, we have seen def double, right? What elements of this expression seem specific to doubling and what elements do not, right? So I have suggested that def is a keyword that does not change. That's non-obvious to you. You've seen no other examples, but you both correctly inferred that. And then you both correctly inferred that if we're tripling instead of doubling, it makes sense to change the name of the function. Now, the names of the functions are not meaningful because I can say def triple.
But what you print, like, print is like what you're explaining what that means. So it could literally mean, like, you could literally say apple.
Yeah, or I typed 3 by accident. But yes, we can name a function apple after, of course, the hit song from Charlie XCX on Brat. Are we all?
I don't know.
Okay, all right, that's fine. You're not required to like Charlie XCX. She's a millennial. Okay. We'll cube that. What's 3 cubed?
27.
Or that.
3 squared is 9, right? Okay, so we have Apple. Y'all really don't listen to Charlie XCX? Do you listen to like cool music or like weird music? Never mind, I can't ask you that. Never
Like
mind.
in the past,
Yes.
like,
Yes.
underscore random music.
Random music, that's good. Yeah. I got really into throat singing for like 2 weeks and then I just stopped. I don't know why. Huh?
Like the Who?
Yeah. like wolf totem or something as well? Yeah, okay. Okay. There's an apple, now I'm hungry. We were talking about vegetables earlier. I'm like looking at the apple. Right, so, okay. I hope it doesn't fall far from the tree. Okay, so that's how we create functions. Here's a metaphor. Def is like asking a friend for something. Hey, can you add x and x together? Do you need to know what x is to do that?
Yes.
Okay, here I'm giving you my favorite x. My favorite x is -4. Can you double that for me?
As in -4 plus 4? Or -4 plus -4? Or -4 times 2?
Right, this is why you have to be specific. Do you have a favorite?
Plus
Okay, well, what's -4 plus -4?
-8.
That feels like doubling -4 to me, right? Like if I were missing 4 things, then I was missing twice as many. I would be missing 8 of them, which in this case would probably be like my marbles, which I have lost. Okay, so I can say, can you print out the result of x and x? So I could ask you to print out a piece of paper that says -8 on it, right? Yeah, so we can do that because we're friends. And so this is sort of the extended metaphor for how def works. Versus printing, there is another way to get solutions back, and this is weird and strange. When we print something, the computer shows it to us. When we return something, it changes the result of the expression. So, we have looked at expressions before. For example, 1 plus 1 is an expression. We can store the result of that expression in a variable. Oh, that's not what I meant to type. X equals 1 plus 1. No, why do I keep hitting plus? Okay. Oh, it's on the same key. Did you know that? I didn't know that. Okay. I was holding down shift the whole time. Okay. So I can take an expression and I can store it inside a variable. And oftentimes I do this when I want to use it later, right? So then I can look at the value of x. This is much more similar to returning a value, giving a value back to the person that is evaluating the expression, than it is to printing. And I can show you an example. We can also print 1 plus 1, which may superficially look the same as just evaluating 1 plus 1. But if I try and put them inside a variable, I am going to get different actions. So if I say x equals print 1 plus 1, I'm going to see 2, right? And this should seem a little bit different to us already because we've previously seen up here that when I do x equals 1 plus 1, I do not see the 2. The reason for that is, in this case, the 2 that exists is hidden inside the x, and in this case it is not. In this case it is given to me. So when I print things, I give them to myself. What this means also is that there is no value in x at all. So I can add, for example, I can't add these together. There's not a number in there. But if I set x equal to 1 plus 1, then I can add those together because they're numbers all the way down. The real reason to use this is just for the example of our piecewise function. So we can rewrite our piecewise function using return instead of print. You can look at this as a bit of a brain teaser later. I'm going to use the small example of the double function again, which I believe I still have double. Okay. So we've been doubling things, and sometimes we might want to double something twice. For example, I gave the example of, I think at some point in human history the interest rate was such that your income would, or that your savings would double about every 7 years if you invested them in like an index fund in the stock market or something. I don't know if this is still true. But if it is the case that your savings double every 7 years, then we can calculate how much your savings double by or how big they are in 14 years by just doubling it twice. I don't think that works for us now. Oops. Double, double, 7. And I would kind of like that to work, right? But what I actually do is I see 14, which is from doubling 7, and then I get an error because this doesn't make sense. What double is doing is when we define double, and I'll just type it again so we know what it looked like. We printed either x plus x or x times 2. I don't recall which one. That expression was not going to have any value in it. So if I set y equals to double 7, I will instantly see the 14, and there will be no numerical value in y. But I can change that by switching from a print statement to a return statement. Now, this return is going to be structured slightly differently. It's going to be closer to if and def. It is not going to have the parentheses in it. So I'm going to write this out. Def double x. I'm going to return x times 2. When I do this, I'm going to see slightly different behavior. If I take y equals the double of 7, I am not going to see 14. But if I double y again, I am going to see 28. And the reason for that is that double 7 is no longer telling me anything. Rather, it's telling the computer something with return. Is that confusing? Correct. Good job. Yes. Okay. Do not allow yourself to be tricked into thinking this isn't confusing. You just have to outsmart it, right? And so this is the example I just stepped you through. It's here on the slides, and I think it is basically unremarkable other than that. We're going to use this to resolve the piecewise problem. And I'm going to do so by taking def and piecewise, and I'm actually going to type through this. Let's see if I can, okay. I'm going to type out how I'm going to do this so I can narrate it. So I can type def piecewise. I have to give it some name. I'm calling it the piecewise function. You can call it whatever you like. It is completely reasonable to call this f. If x is less than 4, and I'm going to put that inside parentheses because I'm trying to see if it is true or false, I'm going to not print but return 9 times x squared plus 5. I think that's correct. If 4 is less than or equal to x is less than or equal to 8, I'm going to close my parentheses, and I'm going to do a colon at the end of my line. I'm going to press enter, and I'm going to indent, because I have to indent after each one of these sort of special keyword statements. Then I'm going to return, it's just 9, okay. Oh, and that should be else if, but I think that's okay. I think this will still work. And then if x is greater than 8, I'm going to have a colon at the end of that line. I like to think of it as every time your line of code ends, you have a frowny face because you're sad that you're done writing code, right? I think we can all relate to that experience. Okay, I'm going to return 2 minus x. And then I can calculate f of x. I can calculate f of negative 1. I can calculate f of 4. I can calculate f of 5. I can calculate f of, I think we did 9. Does that sound right? And maybe 11. It's cut off on the bottom of the screen here. But now, I don't want to speak for the rest of you, but I think we can all agree that this is objectively really cool, right? I'm not hearing loud agreement, so I'm going to take your silence as an affirmation, okay? This is why no one lets me run elections. Okay. I found it annoying to write all of those different f's more than once. If the pitch for using scientific computing is that it's easier, and we don't have to work as hard, we shouldn't be doing the same thing over and over again, right? And we're going to solve this with something called iteration. It doesn't matter what it's called. What it means is that we get to do things over and over again. I don't know if you will have necessarily seen a set. I think of set as one of the first things you sort of learn in college mathematics. It is an unordered collection of elements. What is an element? The element is the thing you put in a set. Specifically, we are looking at the set negative 1, 4, 5, 8, 11, which means the elements are numbers. So I can take this and I can create a set called S. I don't know what I'm typing. Oh, hey, it's like a presenter view. See, it's timing things. Okay. So I'm going to create a set, and it's going to contain -1, 4, 5, 8, and 11. And I can just do that in Python, which is kind of magical. But one of the issues, or perhaps not an issue with this is very fuzzy. But in fact, these numbers appear to be in a different order than those numbers. And that's because a set is an unordered collection of elements. The order is not preserved. This can be quite annoying or not. But what we can do is we can just see if this thing's a set. We can ask the type the same way we can print it. There's some built-in ways we can examine sets. Perhaps can we add it to itself? No, we cannot. Can we double it? Oh, no, that's X. Okay, can we double S? No, we can't double that one either. But we can do certain things to sets, and there's other things we can't do, right? So sets join integers and booleans as the types of things we can have inside our computer, and I think types that you cannot have in your graphing calculator. Once we have a set, we can introduce our final critical breakthrough thought of the day. And this is the for loop. I think of the for loop as the, fundamental building block of computers being useful. It allows to automate repeated tasks. With the Python for loop, we can take an action for every element of a set. And this is really cool because this means we can compute the tax level of every income in the United States without having to type them all in more than once, right? So we're going to use a for loop. There's a lot of bullet points on this slide, but what we're going to do is it's going to be very similar to def, very similar to if. We're going to type for. We're going to type a space. We're going to type the name of the element. The name of the element is going to be the same as the sort of alias or name that we use temporarily in a function definition. So when we doubled x, we can say for x. After we give the name of the variable, we're going to say the in keyword. So for every for, there is an in. And then we are going to give the set or collection, and then we're going to end with the colon special character, and then we're going to indent a new line of code. So we can say for x in s. And those are the four things: for, a name, in, and a set. We're going to do a new line, we're going to indent, and then I'm just going to say we'll print x squared. No, we'll print f of x. That's fine, right? Two parentheses there because I'm looking at f of x. I'm calculating f of x, and then I'm going to print it out. And so these are all of the 9s, the -9, and the 14 that we got from our original solution, but they're in sort of the wrong order, or perhaps the unexpected order. And so that is the same solution I see here. And we can also just look at the elements directly. There we go. 4, 5, 8, 11, -1. And this doesn't look particularly that unordered to me. It looks like they just put the negative numbers at the end. That's easy enough to work with. And how do we solve this problem? We use lists. We just write them a little bit differently. I'm going to say, I'm going to take a list. Now, okay, I would usually call a list L, but that looks almost indistinguishable from a 1 to me. So I'm going to call it, we'll just call it A. And I think my values were -1. I'm actually going to see what the values are. Okay. A is going to equal -1, 4, 5, 8, 11. And then I'm going to say for x in A, print f. I hit caps lock, did I? No, I was holding down shift. And this gives me the 14, 3 9s, and the -9 that I wanted sort of at the beginning. And it does it, by the way, in only 2 lines of code. I'm not hearing any oohing and ahhing. Ooh. Were there was there a round of applause perhaps? Oh, no, okay. No, you don't have to start applauding because someone asks for it, okay? I appreciate it. You're being too kind. Okay.
I applauded in my head.
Is that better or worse?
I don't know.
So you were thinking about applause?
Yeah. I
Do you-
just need to put that out there.
Yeah. I appreciate that. I'll think about your thoughts. Okay. This solves the problem we have. For element in collection do thing. They are now in order. I'm dehydrated. I'm looking at that water bottle, and I'm feeling envy in my heart, which you're not supposed to do. That's bad. Okay, so one nicety we can do here is we can print out lists. I can print A, and it shows me my list, which means that we can, for x and A, we can print not just f of x, but we can also print the incoming x value. And that might be really cool. Like, this would have made 8th grade a lot easier for me if I knew how to do this, but I didn't know how to do it in 8th grade. This is kind of a cool thing. And then, lastly, when you have a list, you can change and update its values. And we do this using its addresses. Do we have actually time to do this today? No, we don't. We'll talk about this some other time. I think I'm concerned I've done too much content today, so I'm going to stop talking. They're done at 5:30? Okay. I think the three of us are going to walk around, and I have to review all of your names, and then we're going to let you go at 5:30. Yeah, if you want to ask me any questions about lecture today, we'll do that. This is a good place to stop. I'm going to start here next time at slide 53. Okay, I'm going to stop the recording, and then I'm going to review your names, and hopefully you can all get to meet Claire as well.